Hello and welcome back. We now continue our series on neural networks and deep learning and focus on self and semi-supervised learning. So far we've encountered unsupervised learning and supervised learning. In unsupervised learning we had no labels, but we learned the structure in the data, for example in clustering. We also could reduce the dimensionality of our problem using principal component analysis or in autoencoders or latent space representation. In supervised learning, on the other hand, we had a label or a true assignment for each data point. And essentially what we did was learning the mapping between the features and the labels. In order to be able to do supervised learning, we need to create those labels. Essentially, we have a lot of data, for example images, and then some humans that spend a lot of effort on manually labeling all those data so that, for example, the image of a cat would be labeled as cat and so on. And then we use our big, complex, deep learning neural networks and apply these to new images, and we would be able to classify an image, for example. However, the effort that goes into labeling these images is substantial. And in many cases, this labeling part seriously impedes a project because so much effort is needed to create an appropriate training data set. So it would be great if we could sort of at least reduce this or avoid it. And this is what self and semi-supervised learning is about. In self-supervised, we don't need any labels. In semi-supervised, we need a few labels. So let's look at a few approaches that work towards this direction. One of them is called consistency regularization. That means that predictions should stay the same after adding some noise or performing some augmentation. So here, if we have an unlabeled image and we have some model that predicts an output, then we get, for example, a prediction, dog or cat. Then if we do something to that image, like for example flip it around or add some noise, then the prediction will change. And the labels should still be the same. So this helps us to identify if a label for a given image is, for example, good or bad, or if we have an unlabeled image, what it might be, because these different augmentations should not change the label. One way that we can exploit this is called fixed match. We have a few labeled images and we sort of weakly augment unlabeled images. And there we use then this as a pseudo label for strongly augmented images. A weakly augmented image is, for example, that we rotate it slightly or add a little bit of noise so that it's quite the same as before but a little bit different, like weakly augmented. And strongly augmented means that we transform the image more drastically, for example, changing its color. Then we combine all our labeled and unlabeled images to improve our training model. So for example, we have the same image of a dog here and we don't have a label for it. And we take this image and do a weak augmentation for it, for example, a flip or a shift or a little bit of noise. And then our model will give us a prediction and we have a cutoff value and say this is a dog. So this gives us the pseudo label that we can use then on a strongly augmented images that is heavily distorted, for example, by changing all the colors. Here the prediction is not quite the same. As you can see, none of these two predictions, cat or dog, will pass our threshold. But because we already have a prediction from the weakly augmented unlabeled image on our previous model, now we can have this as a so-called pseudo level. So we treat the prediction of the weakly augmented images as the true label, and then we proceed and iterate. Of course, we need a starting point. Here we rely on supervised learning, but we don't label our whole data set. We start with few labeled data. So we have, as before, our labeled image. We train our first model, make a prediction with a true label. And then we start to add more and more unlabeled images. And of course we need to make sure that we don't learn any wrong wrong relationships. Another approach is called contrastive learning. The key idea here is that we let the networks learn what is similar and what isn't. So we can compare this to our intuition. We have here 3 images of a cat, and they are not quite the same, but we can identify that these are more similar than, say, for example, the image of a bird. So what we need to have in order to be able to say what is similar or not, we need to have a representation of the image. This is our latent space, and some sort of similarity measure. And there are 2 main approaches that have been developed, SimCLR and MoCo. Let's have a closer look at how SimCLR works. So we have our image, and again we augment these images, for example, by flipping and rotating it. Then we use an encoding convolutional neural network, for example the first part of an autoencoder with the CNN architecture. This gives us image representation. And then we can put this into a dense net, and we can compare the similarity. And the network discriminates then between which of these image pairs are more similar to each other compared to other combinations. So we would augment our images, for example crop or flip, shift, or change the colors and so on. So we have several sets of images that are similar to each other. But these sets are different across sets. So starting from our cats, we would have a set of augmented cat images, and we would have a set of augmented bird images. So of course all the cats in the cat set would be more similar to each other than to all the birds, and vice versa. So we feed all these images into our encoder, for example our first part of the autoencoder. This gives us the numerical essence, shall we say, or the latent space representation. We also then add the projection head, where we convert these base representations to a new representation. And this is then what we use to compute the similarity measure. For example, we can take the cosine similarity. Essentially, we take the latent space representation as a vector and calculate the cosine of this. And then this network will learn that, for example, cats are more similar to each other than birds, and birds are more similar to each other than to a cat. Finally, we will get a trained network with this approach, where we have representations that encode the image classes. Of course, these are then just sort of the representations in network speak, and we need to connect this somehow to our human world. And for this we need to fine-tune the network on very few labeled images, so that we can connect human readable class names with what the network has found out. Another approach is called self-labeling. The intuition behind this is that we repeatedly train networks to generate labels used during training, and the starting point is a randomly initialized neural network, for example a convolutional neural network for image classification. So we have 2 steps that we repeatedly use. We train a new network that gives us in the application labels, and then we use the labels to train a new model. So how do we do this? As a preparation, we need to obtain, for example, the images and play our image augmentations again. Then we need to define the number of classes we want to discriminate between. That we can either do using domain knowledge and say we already know that we have n classes that we need to separate in those images, or we set this as a free parameter and need to then vary this parameter and see how this behaves. We also need to define our network architecture. And again, we have an encoder, for example, for images convolution neural network, that gives us a latent space representation, i.e. the numerical essence. And then we have a classification part in the end. Remember that we want to discriminate between the different classes in the images. So essentially, the lower part here explains our chain. We have the images, the convolution neural networks create us, shall we say, the features that are used in the classification, and we specify the number of outputs that we want to have. Initially, we don't have the labels, so we start with random label assignment. And then we need to optimize this assignment in a special way. And this essentially says which image belongs to which class. And then we repeat and iterate, and this generates both the labels and the network. And again, because the labels are now sort of computer speak, shall we say, we need to connect this to our human readable labels. And for this, we fine-tune the fully trained network on few labeled data to connect our human understanding of what these labels are with what the computer has determined.